Consider a uniform ladder that rests against a smooth vertical wall. Smooth means there is no friction, but the floor has a friction, and the coefficient of a static friction, mu s, is given to us to be 0.40. So our goal in this problem is to find what is the minimum angle theta that will allow this ladder to stay still and not to slip. So which means, what does it mean, minimum angle theta? So that means that the ladder should stay in equilibrium, which means stationary and not moving at this case. So for that, we have to write equilibrium conditions. Equilibrium conditions. So which says sum of the forces on the x-axis, that net force, equals 0. Sum of the forces on the y-axis equals 0, and sum of the torques also equals to 0. So to be able to use these equilibrium conditions, we have to figure out what are the forces that act on this ladder. So ladder is uniform, therefore its weight is can be located from the center. So this is the mg, and then we know there is a normal force from the floor, so let's call it N1, and then there is another normal force going perpendicular to the smooth wall. It's called N2. This seems like and there is also a force, friction force, that goes this direction. So try to think, why would the friction go to the right? So if you consider the situation in a real life, you will see that the ladder will slip and go further away. The bottom part will be going away from the wall. So the static friction would be the opposite direction of the motion. Okay, now let's go ahead and write the sum of the forces by x. Well, let's choose our x and y. So I'm going to call this to be positive y and this to be my positive x. Okay, so, and then of course we're going to consider counterclockwise to be positive. Okay, so now sum of the forces on x. On x we have N2 and Fs. So I'm gonna say Fs minus N2 equals 0. Sum of the forces by y, I have N1 that is positive minus Mg that equals 0. And so for the torques, I have to write the torques by sum of the torques about a point. So I'm going to choose a point to be right here. So why do we choose point O, the torques? Because that will eliminate N1 and Fs when you calculate the net torque. So I'm going to go ahead and write the torques. So that would be, let's just write what are the torques. So we have the torque created by N2 force, which equals I'm going to talk about the sign later, hold on. So that's an N2, and the lever arm will be, if I know the length of the ladder is actually an L, so the lever arm, as you can see, the lever arm would be L times sine theta. And then N2 actually will rotate the ladder in a clockwise direction. Therefore, it has a positive sign here. Okay. So now torque by mg. Mg will rotate the ladder clockwise, not counterclockwise, so therefore the torque is negative. So I'm going to put a negative sign in here. Okay. And then that would be mg, and the lever arm will be L over 2 cosine theta. Okay, so torque done by the normal force 1 equals 0 because lever arm is 0. Torque equals by the friction force is also 0 because the lever arm is 0. Okay, so now we're going to add them all together and write as a sum of the torques. So I would have torque of N2 plus torque of mg plus torque of N1 plus torque of friction equals 0. So let me just separate this a little bit here. Then plug in the numbers. So I have a positive N2 L sine theta minus mg L over 2 cosine theta equals 0. Okay, so from here I can say N2 L sine theta equals mg L over 2 cosine theta. So you can see that the L's cancel out. Remember, my goal is to find the theta. So then I will write sine theta over cosine theta, all the terms with the theta together, equals mg over 2n2. So that makes it tangent theta equals mg over 2n2. Now we're going to go back to the first equation that we had originally. So let's call it first equation and then second equation, and find the n2 from the first equation. Okay, so n2 from the first one, n2 equals static friction. But then we know that the static friction also equals mu s times n1. Now from the second equation, I can find what is the n1. So n1 equals mg. So plug this one into here. I will get mu s mg. Okay, so now I can plug this one back into my original equation for tangent theta and solve for theta. So from here I can say tangent theta equals mg divided by 2 mu s mg. Well, guess what? mg's cancel out and we have 1 over 2 mu s. So from here I can find theta equals tangent inverse 1 over 2 mu s, and then we're going to plug in the numbers. We'll get the tangent inverse 1 over 2 times 0.40, which equals 51 degrees. So this would be the minimum angle that we need to provide so the ladder doesn't slip.